Welcome back to David's Math from Home. This is part 3 of our video on line integrals. In part 1 we did functions, functional paths. In part 2 we did paths that were straight lines. And here in part 3 we're doing paths that are vaguely circular. So circles are probably the most complex of the paths to parameterize. If you're going to parameterize the circles, you need to use sines and cosines, and you need to know which one to use for x and y, and whether or not they're negative, and where they start and where they end. So a lot of parameterizing circles is going to come down to the start and end point of the circle and the direction you're moving around the circle. If you're going clockwise is sort of standard for sine and cosine. Counterclockwise is going to give you weird things. And yeah, start, the end point, the size. You can end up with lopsided circles if you want to go like ellipses. We talked about how to parameterize all of these things in chapter 12 of this book, I think. Right at the end of Calculus 2, we did pretty much all of this material in terms of parameterizations of things. So check those notes if you need a refresher. I can link the videos I made for those sections on the canvas if you want to see those as well. This path right here is relatively straightforward for us. For this path, we want a semicircle counterclockwise. We want it to be, oh, if it's radius 2, it's got to start here and here. Okay. We want it to have a radius of 2. We want it to start 2, 0 on the x-axis. Let me use red for the path. That seems to work well. We want it to start at 2, 0 on the x-axis, and we want it to go counterclockwise around to negative 2, 0 on the x-axis. This is my semicircle. It's going to go halfway around from 2, 0 to negative 2, 0. We're going this way. So hopefully we can sort of already recognize that this is very much like a unit circle, but twice as large, and we're only going halfway around. So the parameterization of this, the parameterization of the unit circle would be r is cosine t sine t. You use cosines for x's, sines for y's. That's the standard parameterization of the unit circle. That's what we've been working on since pre-calculus. This is going to be the same because we're starting in the same place as your standard unit circle, and we're going in the same direction as the standard unit circle, except we're going to make it twice as big. So I'm going to say that r is 2 cosine t, 2 sine t. This is my x value. This is my y value. This is my parameterization of my curve. This vector field, on the x, it's always going backwards pretty gently. On the y, it sort of converges to this line. So you'll see things that go, if you're close to this line, you're going to have a very small y component, and you're just going to have that x component that pushes you backwards. If you're far from this line, you'll have things that move you towards the line, but the x is still going to push you gently backwards. So I'm expecting a decent-sized positive result, because my path is moving to the left and my vector field is pushing to the left, so we should get a pretty positive result from this, I think. Over here, a lot of it is pushing in the same direction. Over here, we're going to be kind of going against it, because the vector field is pushing up and my path is going down, so maybe after we do this problem, oh! We didn't even finish this parameterization. We need bounds on t. To do the full semicircle, where we're going to go with the vector field up and then sort of vaguely against the vector field as we go back down, but still moving to the left. To do the full semicircle, we need t to go from 0 to pi. Although I'm very interested, after we finish this problem, to see what happens if we go from 0 to pi over 2 and end this path a little early. Maybe we'll get a bigger number. It's hard to say. I'm curious to find out, though. So we have a parameterization. We need the derivative of that, which is going to be -2 sine of t to cosine of t dt. We need to rewrite f in terms of t. F of t. Rewriting -1 in terms of t doesn't change it. -1 is still just -1. That's a constant. This stuff, we need to express 2 minus y as 2 minus 2 sine of t. 2 sine of t is my y value, so this becomes that. Next up, we need a dot product. F of t dot dr should give us 2 sine of t plus 2 minus 2 sine t times 2 cosine t. I'll toss a dt at the end of that. So simplifying this up a little bit, I'm going to have 2 sine of t. This should give me 4 cosine of t. And I'll get -4 sine t cosine t dt. This is my dot product. So, in step 5, I need to integrate that. The integral over the path of my vector field times the little pieces of my path is the integral from t equals 0 to t equals pi of 2 sine t minus plus 4 cosine t minus 4 sine t cosine t dt. Now we just have to integrate. 2 sine of t integrates into negative cosine? Yeah. The derivative of sine is positive cosine. The integral of sine should be negative cosine. So -2 cosine t plus 4 sine of t minus 4. We have to integrate sine t cosine t. If you're not sure how to do that, then you should go back to some Calc 2 videos I made when we first started talking about integration by parts. Because sine t cosine t is my favorite integral in all of Calc 2. There's 2 ways to do it. You can do it by parts, but doing it by parts gets really weird. It turns into an equation where you have to subtract the integral from both sides and then divide it by 2. It's really, really cool. If you've forgotten it, you should go check out that video. The other way to do it is to do it by substitution, where you assume that this sine piece is actually to the first power. So your inside function is a sine, your outside function is something to 1 power, and your other function is a cosine. And what you end up with in either case is 1/2 sine squared t. And we're evaluating this from 0 to pi. When you get your trig functions involved with this, you have to be very careful. In the last couple examples, we just had polynomials, which always had these t's involved, so we could pretty safely ignore the evaluate at 0 part. When you evaluate those polynomials at t equals 0, everything just zeroes out and you don't have to subtract anything. But here, we need to evaluate it at pi and we need to evaluate it at 0, because the cosine of 0, for example, is going to be an actual thing. So, let's see what we get here. -2, the cosine of pi is -1, so this is going to be 2. The sine of pi is 0. This is the sine of pi squared is 0, so that's all still just 0. Okay. Then we evaluate it again at 0, and we get minus. The cosine of 0 is 1, so it's going to be -2. Sine of 0 is 0, cosine of 0 is 0, so yeah, just 4 sorry, 2 minus -2 is 4. So, as we expected, we got a positive number from going, the vector field kind of pushes us this way. We were going in that direction sort of more or less anyway. I'm still really curious to figure out what happens if we only do the quarter circle and stop here. And the nice thing about all of this work is, now that I've got it all, the only thing that actually has to change for me to find that out is, instead of going all the way to pi, I can just go to pi over 2. And I'll swap this out for pi over 2, and I'll swap this out for pi over 2. And I'll do another one of these. If we take the same integral from 0 to pi over 2, then cosine of pi over 2 is 0, so that's fine. The sine of pi over 2 is 4, or sine of pi over 2 is 1, but we multiply that by 4. This is 1 times 2, and that's negative. Minus cosine of 0 is still -2, and the sine, that's still 0, that's still 0. So this is actually, this is the same thing. I was not expecting that. That's like legitimate. I didn't do this beforehand so that I could trick you into this cool thing that just happened. That was legitimately a surprise to me. Apparently, going from here to here is a network of 4, and going from here all the way to here is also a network of 4. So I bet if we went from here to here, we would get a network of 0. I will leave that for you to discover. See what happens if you evaluate this integral from pi over 2 to pi. I bet you get 0. That's really cool. Anyway, that's going to do it for me. This has been line integrals in 5 easy steps. Parameterizing the curve is probably the hardest one. Sometimes, if you have straight lines, that goes real smooth. If you have functions, it tends to go real smooth. If you have circles or round things, it gets a little bit more complicated, but we've practiced with circles and round things before in Calc 2 when we did parametrics there, so hopefully that's not a big surprise. If you need more practice on that stuff, let me know. I can link those videos, I can make those homework assignments available so you can practice on those a little bit. Once you've parameterized the curve, there's 4 other steps, but all of them are very straightforward, and they're all things that you've done in calculus 100 times before. You take a derivative, you know how to take a derivative. This is effortless. You substitute your variables. Again, effortless. This is your x variable, this is your y variable. Just put them into your function, your vector field, make it a function of t. Take a dot product, you've done dot products. Dot products are the easiest way you can combine 2 vectors, and then you integrate. Seems like a lot, it's not that bad, it's pretty straightforward. Good luck.